Hello, welcome to today's class. And in today's class, we are going to be talking about implicit differentiation. Um, when is a function said to be implicit? For instance, if I have y jointly bound with x in a given equation, more of like a mixed equation, and I'm asked to differentiate y with respect to x, that is said to be an implicit function. For example, if I have the given function xy squared plus yx squared plus 3 equals 0. This is kind of expressing y as an implicit function of x, simply because I have both y and x actually bound together. Such an equation would appear like this is called an implicit function. And of course, the idea to differentiate this function is simply the idea of product rule. From product rule, you simply know that if I have y to be equal to uv, and then we simply say that the x is simply equal to, the rule simply says you keep u as a constant and you differentiate v, so you simply have dv with respect to x plus, now you keep v as a constant and you differentiate u, you simply have du all over the x. So this is actually the basic idea that governs implicit differentiation. When you have x and y being bound together and you ask to differentiate y with respect to x, since they are joined together, you simply employ the product rule of differentiation to carry out um, that derivative. For instance, for the given question on the board, I have xy squared plus yx squared plus 3 to be equal to 0. Now, when differentiating, you consider both x and y to be a function of x. Okay, since it's an implicit function, you consider both x and y to be all functions of x. And as such, you differentiate both x with respect to x and you also differentiate y with respect to y. Okay, for instance, let's say we have this question now and we are asked to differentiate. From the law, I simply have y equal to uv. Now I'm having xy squared. So I will treat x as my u and I will treat y as my v. And I want to differentiate this function. The law simply says keep u constant. So which means I'm going to hold x as a constant. I will simply keep x constant. Then I will differentiate y with respect to x. So d dx of y squared. I'll differentiate y squared with respect to x plus, now you keep v constant, which means I'm going to be keeping y squared as a constant. Okay, then I'll differentiate x with respect to x. So that's simply differentiating with respect to x the function x. Okay, plus, same thing goes here. I will keep y constant and differentiate with respect to x. I will differentiate x squared with respect to x plus, now I will keep x squared and then I will differentiate y with respect to x. So I will simply have d dx of y, then I will differentiate the constants plus d dx of the constant 3, and the whole of this is equal to 0. So when carrying out implicit differentiation, you simply consider both x and y to be a function of x. Okay, so having that in mind now, I will simply have x. Now, I want to differentiate y squared with respect to x. Remember, to differentiate a function, simply use the power to multiply the function itself and then subtract 1 from the power. So I will simply have x times, I will use the power, which is 2, to multiply y. Then I will subtract 1 from the power. 2 minus 1 simply gives me 1. So that simply means I have 2 minus 1. Then I will simply put down the y all over the x, simply because I'm differentiating y with respect to x. All right, so plus, now you keep y squared constant and you differentiate x. Of course, if I differentiate x with respect to x, I will simply have dx all over the x. Of course, dx all over the x, that's what it gives me. Okay, plus, next you keep y and you differentiate x squared. So to differentiate x squared, of course, use the power to multiply the variable itself. So I'll simply have 2 times x, but then I differentiated x with respect to x. So you simply put down the x all over the x because I differentiated x here with respect to x. Okay, so plus, same thing here, this becomes x squared. Okay, Now I'm differentiating y with respect to x. Y does not have any variable attached to it. Y does not have any power attached to it, so it still remains dy all over the x. Of course, if I differentiate y, I will simply have 1. So 1 times the y over the x. Okay, now I have d over the x of 3, and 3 is a constant. The derivative of every constant, of course, is simply 0. So which means I will simply have this to be plus 0, and that's equal to 0. So if I evaluate this now, I will simply have this becomes 2x. Of course, 2 minus 1 here is 1. So that means that simply gives me 2xy. We have 2xy for here, dy dx, 2xy dy all over the x, okay, plus y squared. Of course, the x over the x is 1. So that's simply up. I'm left with simply plus y squared. Okay, next here the x over the x as well here is 1. I will simply have here 2xy plus 2xy. Okay, here I have x squared dy dx, so plus x squared dy all over the x, and the whole of this is equal to 0. But not forgetting, the aim is actually what? The aim is to actually find dy dx. So which means at this point, all I need to do is simply what? Collect like terms. Let the terms that have dy dx actually come together. So I'll simply collect like terms. And if I do that, I have here 2xy dy all over the x. I also have here x squared dy dx. So I'll bring them together plus x squared dy all over the x. Okay, I have here plus y squared plus I have here 2xy, and this is equal to 0. So from here now, notice that dy dx is common. Notice that dy dx is common, so I'll simply factor dy dx. So this simply becomes 2xy plus x squared all multiplying by dy all over the x. Okay, plus y squared plus 2xy, and that's equal to 0. So the aim, as always, is to obtain the value of the y dx. So I'll simply transfer every term here which does not contain the y dx to this side of the equation. If I do that, I'm left here now with 2xy plus x squared multiplying through by the y dx, and this is now equal to, of course, if I send y squared over here, it becomes minus y squared. Also, if I send plus 2xy over here, it becomes minus 2xy. So from here it's easy. I can now make the y dx subject simply by dividing through by the whole of this term. This simply implies that the y dx itself is simply minus y squared minus 2xy all over 2xy plus x squared. So you simply have this. So whenever dy dx, so whenever y is expressed as an implicit function of x, all you need to do is simply employ the product rule and carry out that derivatives between the two of them. And also keep in mind that you always treat x as a function of x, you also treat y as a function of x. So which means you're differentiating these both variables all with respect to x in order to be able to find the y dx. Let's try another example and see. So let's try this other question on the board. We have that x squared plus y squared equals r squared, and we are asked to find the y dx. Now this is also an implicit function simply because I have y squared and not y. Now this is more like simple function or simple implicit function per se, because I can actually want to make y a function of x since y is not jointly attached to x. Okay, but I think if you encounter such a problem, the best thing to do is always take the approach, make y to be what? A function of x directly. Since y is not directly attached to x, you can simply make y the subject formula. From there, you can start. Now, let's say we want to make y squared subject of the formula. Simply send x squared over to this side of the equation. I will simply have that y squared is equal to r squared minus x all squared. And now, of course, I can proceed to make y subject. Y will simply become equal to the square root of r squared minus x all squared. I can simply have this. And of course, you know that you can write this simply as this simply means y is equal to r squared minus x squared, okay, all to the power of 1 all over 2. I can also rewrite the whole of this function as this. So this becomes more simpler than the first question we saw, simply because y now has been made a direct function of x. So I can actually apply the basic trigonometry. So I can actually apply the basic rules for differentiation to actually what? Differentiate this given equation. All right, so here now, the very easy approach to this is by simply saying you attach a variable to be the whole of this function in the bracket. So let's simply say let a be equal to r squared minus x all squared. So if I have a to be r squared minus x squared, it simply means now that this simply implies that okay, this implies that y is now equal to, in place of r squared minus s squared, we simply call that a. So y is now equal to a all to the power of 1 all over 2. So I have here an expression which shows function of a function, because from here I simply have a to be a function of what? X squared, since x squared is the only variable changing here. So a is a function of x, sorry to say. And of course, I have here y to be a function of a now. So I have function of a function. Y depends on a and a depends on x from this given equation. So which means if you've been following up my series, I said whenever you have function of function, it means the only rule you can employ is simply the chain rule of differentiation. And how do you obtain this chain rule? I have a to be a function of x. This simply means I can differentiate a only with respect to what? X. Since a is a function of x, it means I can differentiate a with respect to x. Also, I have y here to be a function of a, which means I can differentiate y only with respect to a. And if I have these two derivatives, to obtain the y dx is simply what? To multiply these two derivatives together. And if you do that, we are going to see that dy dx, okay, is simply equal to the y all over the a times the a all over the x. So notice here now that if I join this together, of course, the a can cancel the a. I'm simply left with the y all over the x. So the first thing is to what? Establish this given function. If I'm able to assign a given alphabet to what? The function in the bracket, then it means now that a depends on x here, as can be seen, and of course y depends on a. And if I find a derivative, I can be able to compute the y all over the x. So let's try it and see. So what I need to do now is simply what? Find the y dA and find the a dx. Multiply them together, it gives me the y dx. All right, so from y equal to from y equal to a to the power of 1 all over 2, I can find the y all over the a, and that's equal to, from the rule of differentiation, use the power to multiply the variable you're differentiating. So I'll simply have 1 all over 2 multiplied by a, then subtract 1 from the power. It becomes 1 all over 2 minus 1. So this is equal to 1 all over 2 a to the power of course, half minus 1 gives us minus 1 all over 2. I will simply have this. Okay. So this implies that the y all over the a is now equal to, of course, we can rewrite this a bit. It becomes 1 all over 2 a to the power of 1 all over 2, simply because of this bar here. Okay, so it it turns to inverse, it becomes 1 all over because of this bar attached to the power of 1 over 2 at a. Okay, so this is now equal to, this becomes 1 all over 2 root a. Of course, you can also convert a to the power of 1 over 2 to be what? Root a. Not forgetting that we said let a be equal to r squared minus x squared. This is the value of a, so we can replace that there. It now implies that dy dA is now equal to 1 all over 2 root r squared minus x squared. So you can keep this aside for the right for the y dA. So next is to actually find the a dx. So we have a here. So from a equals r squared minus x squared. You can simply differentiate a with respect to x, that's the a dx, and that's equal to, of course, now r squared becomes a constant, so which means I'm differentiating a with respect to x, so which means since r squared does not contain a term in x, it is to be treated as a constant. Of course, that's actually a reduced term, so it means it's a constant. So if I differentiate minus x squared, I will simply have minus, use the power 2 to multiply x, then subtract 1 from the power, it becomes 2 minus 1. So this simply means that the a dx is simply minus 2x. Okay, you have minus 2x. This gives us the a dx. So if you have this, from what we've established here, we've simply shown that the y dx is simply what? The multiple of these two derivatives. So if we multiply them together, we obtain the y dx. So this simply implies that the y dx is equal to dy dA, which gave us 1 all over 2 root r squared minus x squared, okay, multiplied by the a dx, which is actually minus 2x. So this can be written as dy dx is equal to minus 2x all over 2 root r squared minus x squared. So from here it's simple. 2 can actually strike 2. I'm simply left it minus x all over the square root of r squared minus x squared. So this gives us the value of that given derivative. Okay, so we are going to try one more example for this, and then we can stop the video and try a different other approach on implicit differentiation. Okay, one more example. So let's consider this next question on the board. We have x cubed plus y cubed plus 2gx plus 2fy plus c to be equal to 0, and we're asked to find the y dx. Once again, this is an implicit function. Of course, I have x to the power of 3. I also have y more than the power of 1 up to the power of 3. And then again, I have x here and y also attached in between. So since we have y to have more than 1 power, it makes it automatically an implicit function. So we actually have to employ all the theorems we know to differentiate an implicit function. Okay, so like I said, while differentiating an implicit function, you consider both x and y to be what? Functions of x. You consider both x and y to be functions of x. So, and then you differentiate each of them individually also with respect to x. So to carry out the differentiation, I will simply what? Differentiate this term with respect to x. So d dx of x cubed plus, I will also differentiate with respect to x, d dx of y cubed, okay, plus, of course, 2 and g is a constant. You pull them out, I'll simply have 2g, differentiate the variable x, so d dx with respect to x, also 2f is a constant, pull it out, plus 2f, differentiate y with respect to x, so I'll simply have d dx of y, okay, plus differentiate c, the c all over the x, okay, and that's equal to 0. I'll simply have this. Okay, so if I differentiate x cubed, of course, I will simply have 3x all squared. Simply use the power 3 to multiply by the variable x, then remove 1 from the power. It becomes 3 minus 1, which gives us 2. So that's 3x squared. Now, because I'm doing this for x, I will simply attach the x all over the x, which means I differentiated x with respect to x. Okay, plus Same thing here. If I differentiate y cubed, I will simply have 3y all squared. But since I differentiated y with respect to x, I will simply now attach the y all over the x. Okay, plus this is 2g. Now, x here is to the power of 1, and of course, if I differentiate x, I will simply have 1. And since I'm differentiating x with respect to x, I will simply attach the x all over the x, okay? Plus, same thing here, y here is to the power of 1, so if I differentiate y, I will simply have 1. But since I'm differentiating y with respect to x, I will also attach, this is now 2f the y all over the x. And of course, c is a constant, and if I differentiate c, I will simply have 0. The derivative of every constant is simply 0. So this is simply plus 0, and this is equal to 0. Okay, so from here now, I'll have 3x squared. The x over the x is 1, so it's off, plus 3y squared. I have here the y dx, so attach that, the y all over the x, plus this is now 2g, the x over the x is 1, so you have 2g, plus I also have here 2f dy dx, 2f dy all over the x, and of course 0 is off. This is equal to 0. So at this point, all I need to do is simply what? Collect like terms. I have the y dx here, I have the y dx here. Simply bring them together, and of course take these other terms together as well. So I'll simply have 3y squared dy all over the x, and I send this man over here. It becomes plus 2f dy all over the x. Okay, I have here plus 3x squared, and also I have here plus 2y and plus 2g, sorry, plus 2g. Let's take this off a bit, plus 2g, and this is equal to 0. Okay, so at this point, it becomes easier now. I will simply factor out the y dx, factor the y dx. I'll simply have here 3y squared plus 2f, okay, plus 2f multiplying the y dx, okay, okay, plus this is 3x squared plus 2g equals 0. So what I'll do at this point is simply send plus 3x squared plus 2g over to this side of the equation, so I can be able to find an accurate value for the y dx. And if I do that, I will have 3y squared plus 2f multiply the y dx, okay, is now equal to plus 3x squared crosses here becomes negative, minus 3x squared, plus 2g crosses here becomes negative as well, minus 2g. So I can now make the y dx subject of the formula. This simply implies that the y dx is now equal to minus 3x squared minus 2g all over, I'll simply have 3y squared plus 2f. Okay, that becomes the answer to that derivative. All right, guys, so I'm going to pause the video here. In the next video, we'll talk about implicit functions involving exponential functions and trigonometric functions. Please stick around for that video. Of course, I'm sure you're going to be thrilled with it. I will see you in that video. Thanks and cheers.